Yes. So good evening, everyone. So welcome to the third plenary lecture for Winter School on Deep Learning 2026. So we are very glad to have Dr. Adriana Romero Soriano as our plenary speaker for this session. I, Pratihar, as a senior research fellow of Indian Statistical Institute, is the session manager for this session. And we are also glad to have Professor Swagatam Das, program chair for WSDL 2026, as the session chair. So may I now introduce Professor Das. So Professor Das is currently a professor of Electronics and Communication Sciences Unit ECSU of Indian Statistical Institute, Kolkata, India. He is also serving as a professor in charge of Computer and Communication Sciences Division of his institute for the term from 2024 to 2026. He earned his BE, ME and PhD degrees from Jadavpur University in the year of 2003, 2005 and 2009 respectively. His research interest encompasses deep learning and non-convex optimization, and he has published over 400 research articles in the peer-reviewed journals and international conferences. He has served or is currently serving as an associate editor for seven prominent journals, including IEEE Transactions on Neural Networks and Learning Systems, IEEE Transactions Cybernetics, IEEE Transactions Evolutionary Computations, Pattern Recognition, Neurocomputing, Information Sciences, IEEE Transactions on Systems, Mans and Cybernetics, among and also others. Dr. Das has received over 33,000 Google Scholar citations and an H index of 87 to date. He has actively participated in the program committees and organizing committees of renowned international conferences such as NeurIPS, AAAI, AI Stats, ACM Multimedia, BMVC, IEEE, CEC, GECCO, and more. He is currently serves an ACM Distinguished Speaker. He received the Young Engineer Award in 2012 from Indian National Academy of Engineering (INAE), and in 2015 Thomson Rutgers Research Excellence Indian Citation Award for being the highest cited researcher in engineering and computer sciences in India between 2010 to 2014. Now I request Professor Das to take the stage.
So, good evening, everyone. We are going to start this plenary session for Winter School on Deep Learning 2026. And it's a pleasure and privilege to introduce our today's plenary speaker, Dr. Adriana Romero Soriano, who is a research scientist at FAIR, that is Meta AI, an adjunct professor at McGill University, a core industry member at MILA, Quebec AI Institute, and a Canada CIFAR AI chair. She received her PhD from the University of Barcelona in 2015, where she worked on assisting the training of deep neural networks under the supervision of Dr. Carlo Gatta. Following her doctorate, she completed postdoctoral research at Mila under the mentorship of Professor Yoshua Bengio, focusing on deep learning techniques to tackle biomedical challenges involving multimodal data, high-dimensional data, and graph-structured data. Her research focuses on developing machine learning models that learn from multimodal data, reason about conceptual relations, and leverage active and adaptive data acquisition strategies. Her current work lies at the intersection of generative modeling, computer vision, and responsible AI, with particular emphasis on improving quality, controllability, consistency, and representation diversity in visual content creation systems. Recently, she has been exploring the potential of conditional visual generative models as synthetic training data sources for model self-improvement. Dr. Romero Soriano has made significant contributions to the field, including highly intuition works such as graph attention networks in ICLR, fitnets, hints for thin deep nets, again in ICLR, and instance conditioned GAN in NeurIPS. She has received Best Paper Awards at the CVPR Workshop on Computer Vision in Vehicle Technology in 2017 and CVPR Deep Vision Workshop 2016. Once again, it's a privilege to have you among us. Dr. Adriana, now the stage is yours. Thank you.
Good evening, and thanks a lot for the introduction. It's my pleasure to be here today discussing some of the work that we've been doing with my collaborators over the past couple of years. And so the title of the talk today will be Improving the Utility of Synthetic Vision Data Through Search. So we've all witnessed in the community over the past 5 to 7 years a huge progress in generative models, and in particular for the focus of this talk, we'll concentrate on vision generative models, that is image generative models and video generative models. So if we look back only a few years ago, 2019 to 2021, these were the kind of outcomes that vision generative models were able to produce. So we see that we had like pretty high quality images for class conditional models that were able to produce these images of objects that were centered in the scene, or scenes that are like very specific kinds of scenes, like bedrooms on the slide. Then around 2021, we saw like some big progress moving from class conditional generation to text conditional generation, where provided the text prompt, we were able to generate images that more or less reflected what was requested in the text prompt. Of course, if we look back a few years, we don't see like the quality that state-of-the-art models have nowadays, because we see these images, for example, of the cute cat laying by a big bike, sort of merging some objects, which is something that is has been improved a lot in the recent models. So if we move forward for the last couple of years, this is the kind of progress that we have achieved as a community. So we see that for image generation models, we can obtain generations that are highly realistic, contain a lot of texture and details. And these models are mostly controllable through text, sometimes through text and image conditioning. But it's beyond the image generative models. If we see progress in video generative models, we see in the last year, we've made also impressive progress, where I'm just displaying one of the videos obtained through the generations of a state-of-the-art video generation model. And so given this progress, a lot of researchers have started asking the question, can we actually leverage synthetic data from these vision models to train downstream machine learning models or self-improve the model that is being trained? And so if we think from this perspective, this is the sort of learning paradigm that we have. On one hand, we have the data generator, which is our generative model that is pre-trained, has been pre-trained on a large scale of data and provides an infinite data source. This data generator can be queried through a text prompt, for example, to generate images. And on the other side, we have the learner. We can think of this learner as any machine learning model, a recognition model, a representation learning model, or a generative model, any foundational model for the purpose of this talk that requires vision data. And this model, as any machine learning model, is data hungry and leverages, in this case, the synthetic data that comes from the data generator in order to learn. So this is the index that of the talk that we will follow today. So we will start by asking the following question, which is, are state-of-the-art vision generative models optimized to provide high utility synthetic data for downstream training? And here we'll focus on understanding the progress of image generative models, and I'll present a few analyses that we've been running with collaborators over the past couple of years or so. And then we will move to the question of how can we search the generative models learned manifold in order to find high utility synthetic data. And here we'll see different techniques to explore or to search this learned manifold. And we will see examples of prompt-aligned, diverse, and overall high utility generation of images, physically plausible synthetic videos, or synthetic data tailored to the needs of the learner. So before we start addressing these two questions, I wanted to give some background overview. So the talk is focused on high utility synthetic data, but let's start with defining what we mean by high utility synthetic data. And so we define the utility of synthetic data with the following desiderata. First, the generations should be highly realistic. So here we're talking about the quality of the generations, the images or the videos in our case. The generation should exhibit high consistency with the input conditioning. So if we request something through the text prompt, we want to make sure that every detail of what has been requested appears in the generated data. The generations also have to be highly diverse. So if we're going to use the generated data to train downstream models, we want to make sure that we have sufficient diversity in the generations for the downstream model to be able to generalize. And ideally, we would want the synthetic data to be tailored to the needs of the learner during training. However, state-of-the-art generative models are mostly optimized for human preference. As a result, here I have some generations for a model that is now a year and a half, maybe a couple of years old. And we see what happens when we prompt it for different things. So for example, when we use prompts that have some numbers in it, like two cats and a dog, or two dogs and a cat here, we see that although the images are like very high quality, they do not exactly follow what was requested through the text prompt. And the same happens if we start requesting the model to generate geographically diverse objects, like in this case, a house in Europe, a house in Africa, or a house in South America. So we see that the generations of each one of these regions has very little diversity. For example, characteristics of the generations of houses in South America contain like these colorful patterns. So now that we've defined what we mean by high utility synthetic data, let's have a slight overview on generative models and what they learn. So generative models aim to learn a data distribution. So here it's referred to as P of data. And the most commonly used paradigm for state-of-the-art image generation and video generation models are based on diffusion and flow matching. Diffusion and flow matching models are thus generative modeling paradigms that learn to transform Gaussian noise into samples from a target distribution. So if we focus on diffusion models learn how to denoise the noise towards an image. So they reverse the adding noise stochastic process. So this is what's shown in the figure on the slide. So we start with a forward pass. The forward pass gradually adds Gaussian noise to the real data. So there is no learning involved here. We just take an image from our data and we keep adding noise. Then we have the reverse process that gradually removes the noise by leveraging a neural network. So this is where the training happens. This neural network is trained to predict the noise, or what we call the score function, which determines the drift correction that makes the sample more likely. And we do that at arbitrary steps. So once this neural network is trained, we can generate samples by sampling noise and then repeatedly running the trained neural network to obtain less noisy samples. If we move to flow matching models learn where to move. So instead of learning the noise or how to denoise or the score function to move towards more likely data points, they learn where to move. So through continuous transformations, mapping a base distribution into a data distribution. And they do so by learning a time-dependent velocity field that transports this noise into data. They also leverage a neural network. It's just that in this case, the neural network is going to be trained to regress the direction that moves from the noise to the data. And once this neural network is trained, we can generate samples by sampling noise and again, repeatedly running the trained neural network to move the sample using this velocity prediction. Now, the examples that I covered for diffusion and flow matching models were pretty generic before, but we can steer the generation of these models towards some specific conditioning. So that's when we talk of conditional generative models, where we have, for example, access to prompts or labels describing an image or a video to be generated. And so we can steer the generation process of these models towards the conditionings by modifying the neural network predictions during sampling in the direction of the conditioning. And this is where classifier guidance comes in. So classifier guidance uses an external classifier, which is trained and we use it to steer the generation trajectory. So using this classifier, we determine the direction that maximizes the log likelihood of the conditioning signal. And so here we have the formulation of how to leverage classifier guidance and a visual example of how this could work. So on one hand, we have the unconditional score, which is predicted by the neural network that we train in diffusion models. And this is depicted as the black arrow on the slide. And then we have the classifier guidance term that is making the sample more likely under the specific class or prompt. And so this is the blue arrow depicted on the slide. And so we combine both of these signals in order to obtain what we call the conditional score. So now we have altered the unconditional score that we predicted with the neural network with this guidance, pushing the generation process towards making the generated image more likely to be from a specific class or prompt. So essentially what is happening here is that we are reweighting the model distribution according to the scale probability of the classifier. In flow matching, we can also apply classifier guidance. So we saw that the difference with diffusion models was that flow matching was predicting a velocity field. So we have this predicted velocity field in an unconditional way as the first term in the equation shown on the slide. And again, we can modify this signal by adding the classifier guidance to it and altering the way we move in the generation process. In practice, state-of-the-art models, however, do not use external classifiers like the ones that I've shown for classifier guidance to make samples follow a conditioning. Instead, what we do is we have models that are trained in conditional and unconditional modes simultaneously. So what that means is that we have a conditional mode for the model where the model sees the conditioning. So that would be either the class or the text prompt in text-to-image generation or class-to-image generation. And we have an unconditional mode where the model does not see the conditioning. So during training, the conditioning information is dropped with some probability, such that the model sometimes sees it and sometimes it doesn't. At sampling time, we can combine the conditional and unconditional predictions as follows. So with some weight, we compute the unconditional prediction and apply some weight on it, and then we also compute the conditional prediction. And so we combine both conditional and unconditional predictions at sampling time. In this case, the function f on the slide may be any model output. So it can be the output of a diffusion model, which could be the score function or the noise estimation, or it could be the output of a flow matching model like the velocity field. And here, w is a weighting term. And if we set it to 0, we have unconditional generation, purely unconditional generation. If we set it to 1 instead, we have a conditional generation only. Now that we have a bit of background on what the kind of paradigms that state-of-the-art generative models rely on, so being diffusion and flow matching models, and we also have the definition of high-utility samples, let's see how we can measure these different axes of utility. So in particular, I want to give a bit of context on how we can measure sample realism, diversity, or prompt alignment. So if we start with sample realism, so that would be a proxy for generation quality. And so we ask the following questions. How many generated samples lie close to the reference data? So the assumption here is that if a sample is close in some embedding space to the real data, then it has high quality or it's highly realistic. And so in order to compute that, we use the precision metric. Precision metric requires a set of real data points, so it's grounded on some specific samples of a data distribution, a real data distribution, and it also expects a set of generated data points. So let's assume we have these real data points that are depicted on the slide. And so we want to estimate the manifold of the real data for which we do not have access. So to do that, what we do is look at the nearest neighbors in specific embedding space, such as the Dino V2 embedding space for images. We embed all of these real images and we look for their nearest neighbors. Once we have their nearest neighbors, we take the distance to these nearest neighbors in order to create hyperspheres around these real data points. And once we have created the hyperspheres, we use the resulting volume as the estimation of the manifold for the real data that we have. So once we have estimated this real data manifold, we project into the same embedding space, for example, the Dino V2 embedding space, the generated images. And now we look at how many of these generated images are close to this estimated manifold. More precisely, we look how many of these generated images are within the hyperspheres that we use to estimate the real image manifold. So essentially what could happen here is that even we have the extreme case where a generative model is producing a single image specifically, and this single image is very close to one of the real images, then that would lead to very high precision, because the images would always fall very close, like the generated images would fall very close to each other in the embedding space, and this would be close to a specific real image. So that wouldn't ensure any concept of diversity in the generations. So now let me move towards diversity. So the question that we ask here is, well, how many real data points have generated samples nearby? And so if we, so the measure that we will use here is the one referred to as coverage in the literature. And if we go back to the same idea as for realism, we have this estimated manifold of real data, and we project the generated data on it. Now, instead of checking whether the generated data lies close to the real data, we want to see how many of the real data points have generated samples nearby. Finally, we have the prompt alignment or consistency, as I referred to it earlier. And the question here that we ask is, do generated images follow their respective prompts or class conditionings? And we have a couple of metrics that are very, very popular to measure prompt alignment. The first one is a CLIP score. So CLIP score relies on the CLIP model, a vision language model, which has its vision encoder and its language encoder. And so we feed the CLIP score with a generated image and a text prompt or a class, a text referring to a class. We embed the text part using the CLIP text embedding, and we embed the generated image using the CLIP image embedding. And then we can compute the cosine similarity between the text embedding and the image embedding. That gives us a measure of prompt image alignment. Alternatively, there are also different scores to measure consistency, which rely on visual question answering. So in this case, what happens is that we take the text prompt and we decompose this text prompt into questions and answers about this text prompt. Now, with the generated image, we try to ask the questions about what should be present in this image and compute the accuracy of the VQA. So now that we have introduced this background session, let's move towards the first question that I would like to cover in this talk. So the first question, as a reminder, was, are state-of-the-art vision generative models optimized to provide high-utility synthetic data? And to address this question, I'll try to build some understanding over the next few slides on the progress of image generation. And to do that, I'll cover a few of the papers that we've had in this domain. So the first that I want to introduce is the work that we did on geographic disparities. So this is what we call the DIG indicators that quantify geographic disparities in text-to-image models. And for that, we introduced three different indicators. The first indicator is what we call the region indicator. The region indicator considers two of the dimensions that we introduced as when we defined high utility synthetic data. And these two dimensions are quality, and we're using precision as the proxy for quality, and diversity, where we're using coverage as the proxy for diversity. And I'm depicting in the slide two plots coming from generations of different models with different parameters configurations, that all the squares, triangles, and circles that you see. And I'm depicting results for two different regions. In particular, we plot results when prompting a model for different household objects in Africa and the same household objects in Europe. And what we see here is that for one of the regions, we tend to obtain lower precision and coverage, so lower image quality and lower generation diversity than for the other. So then we introduce a second indicator that allows us to zoom in into this region indicator and do analysis at object level. So that's what we call the region object indicator. And I have here some visualizations of what this indicator may uncover. So again, I'm taking the example of the two same regions that we considered for the first indicator, and we will focus on two specific objects that are car and cooking pot. So for the region where we observed low realism and diversity, so that was for when prompting the models for different objects in Africa, what we see is the following. So the first column depicts real images from objects in Africa that are part of the GeoDE data set. And the second column depicts generations from state-of-the-art models back in 2023, when we did this analysis. And so what we observe here is when it comes to cars, generated images mainly depict SUV-like cars in urban areas. The condition of the car is usually not like the great. And this is by contrast to what we see in the real data set, where we see, instead of rural areas, we see urban areas, more sedan-like cars and in good condition. We have similar observations for a cooking pot, where the generations are mainly outdoor scenes with objects that have like a more rudimentary appearance, and that this appearance does not correspond to what we find in the real data. However, if we go to the region that I chose as an example here, that results in higher diversity and higher image quality, in this case, Europe, and again, we contrast data from the real data set, again, based on the GeoDE data set and the generated data, we do not see this kind of trends. So if we take a look at the third and fourth column for cars, we see in this case that they all appear in urban settings. They are like sedan-like cars and so on. And similarly for cooking pots, we do see that they are all inside in interior spaces, and the appearance is not as different to what we find in the data set as what we have seen for the region of Africa. Now we also analyze what happens when it comes to consistency, so object consistency indicator. And what we did find is that many of the models focus in depicting what they have modeled as the region rather than the object of itself. So in many cases, the model is disregarding the part of the prompt corresponding to the object that they're prompted for, and instead only depicts what they have modeled to be the region. In order to stretch a bit more this analysis, in follow-up work, we proposed the decomposed dig-in indicators, where we focused on decomposing these measurements of geographic disparities between object and background. And we did that in order to capture representation via specific components of images. So instead of computing these indicators that include diversity, quality, and consistency, considering the full image, we decompose the image into different segments, one corresponding to the foreground object and the rest corresponding to the background information. And then we recompute the same indicators only on the regions of interest. So here is what we observe. So when it comes to image quality, so the proxy that we use is precision, we see that we tend to have, on average, higher values for the foreground object than for the background. This is not the case when it comes to diversity. Now, if we contrast the precision and coverage for background segmented and object segmented objects, what we see is that the disparities in the background tend to be a lot higher than for the foreground objects. So if we look at, for example, the triangles, which would correspond to the background information, we see that the leftmost, which is below 30%, and the rightmost is above 50% span the whole plot, whereas if we take into consideration the crosses, like the space that they span is between 35 and 42% roughly. So the decomposed digging indicators help us pinpoint examples of disparities. For example, pinpointing stereotypical backgrounds in the case of some regions, models struggling to generate modern objects in certain regions, and unrealistic placing of objects outdoors. So what were the findings of this analysis? So to summarize, state-of-the-art models, when we ran this analysis a couple of years ago, exhibited performance disparities in real-world geographic representation. And in particular, we found that existing models often have less realism and less diversity of generations of objects when prompting with some specific regions like Africa and West Asia than Europe. Backgrounds of generated images tend to exhibit substantially larger realism and diversity disparities than objects, prompting with geographic information. So adding the regional information to the prompt usually comes at the cost of prompt consistency and diversity of the generated images. And perhaps unsurprisingly, models exhibit more region-level disparities for some objects than for others. However, of notable concern here, we see that from all three indicators, the progress in image quality that we've done as a field in this domain has come at the cost of real-world geographic representation. So we wanted to extend this analysis beyond geographical representation, and that's where we introduced the consistency, diversity, realism Pareto fronts about a year later for text-to-image. So text-to-image, as we've seen with the definition of high-quality data, is a multi-objective optimization problem. So this means that there might not be a single optimal solution to the problem. Objective might be conflicting, and there is a set of optimal solutions in the space of objective functions, which we call the Pareto front. These solutions will, of course, present some compromises, and the solutions that are not present in the Pareto front are considered suboptimal. So let's take a look at some of the results that we obtained. So again, we compare a bunch of models that appeared in the literature, going from latent diffusion models, so that would be Stable Diffusion version 1.5 until Stable Diffusion XL and XL Turbo, which were the state-of-the-art models at the time of this analysis. If we take a look at the Pareto front of diversity and consistency, what we see is that the models that had appeared earlier in time, so the version 1.5, exhibit higher diversity and lower consistency. And as we move towards more recent models, what we observe is that these exhibit higher consistency, but they usually sacrifice in generation diversity. If we move on to the diversity realism comparison here, we observe similar trends where earlier models appear to exhibit higher diversity at the cost of lower realism, whereas more recent models increase realism dramatically, but this comes at the cost of reduced diversity. The picture is a bit different if we look at realism and consistency, so we see improvements go hand in hand, with the most recent models being the ones exhibiting both highest realism and highest consistency. So what this tells us is that there is no single best model, and so depending on the characteristics that we care about, the choice of model should be determined according to this, so according to the downstream application, according to what we care about. Realism and consistency can both be improved simultaneously, and we've seen the progress in this direction for a few years. And there is a clear trade-off between realism, consistency, and diversity. Now, in all of the plots, you will see a few letters, A, B, C, D. So those are models that I'll use to showcase some visual examples in the next slide. So among these models, what we have is model A, which usually corresponds to an earlier version of the model. These models, as we've seen, show higher diversity, but tend to show lower consistency and realism from the plots. Whereas model D is on the other extreme, and so has lower, should have lower diversity, but higher realism and higher consistency. So if we take a look at models A, B, C, D and prompt them for the following prompt, two planes flying in the sky over a bridge, what we see is that, yes, effectively, model A yields the highest diversity, but it struggles following the prompt and providing high quality generations. Whereas we see like intermediate cases for model B and C, perhaps. And if we go to model D, which is the other extreme case, we see that, yes, we have higher image quality and consistency with the prompt for most of the generated images. However, there is very little diversity. The images look very similar to one another. And this is just to show that all of the metrics that we have in this analysis are gathered together in this evaluation library. So if we recap in the information on all of the analysis that we've made, so if we look at models from 2022, almost 2022, late 2021 to almost 2025, what we observe is the following. So first, what we see is that we've done as a community amazing progress when it comes to image quality or image realism. We've also made good progress when it comes to improving image prompt consistency, but these improvements have come at the cost of image diversity. And so progress in image quality and consistency has come at the cost of representation diversity of the generations. Now, what happens if we take the generations from these different models and use them to train a downstream machine learning model? And so for the sake of an example here, we just prompt some of these models, so latent diffusion models ranging from version 1.5 to XL. We prompt them with ImageNet classes and collect data to train an image classification model on this synthetic data. So what we see here when it comes to the achieved classification accuracy is that earlier versions of the generative model yield better results when training a classifier than newer versions of the model. So newer models lead to decrease in classification accuracy with respect to earlier versions in time. And if we take a look at the data scaling law, so what happens if we keep increasing the number of synthetic data points used for classification training? So we see on this plot on the x-axis is the amount of data used to train the classifier, and on the y-axis we have the top one accuracy. And what we see here is that adding synthetic data leads to these diminishing returns. So what we've seen overall with the result of this analysis that I have presented is that, yes, we have improved the image generation realism quality. We have also improved the image generation prompt consistency, but this has come at the expense of representation diversity. And we see that if we use the generations from these models, we also see that newer models lead to worse performance when using synthetic data from them to train downstream machine learning models. And we also see this trend that increasing the dataset size of synthetic data leads to diminishing returns. So this covered the first part of the question that we posed earlier about understanding the progress that we've made as a community in the image generation domain. And now I want to move towards the second part of the talk and focus on how can we search the generative models manifold in order to find high utility synthetic vision data. And so let's start with a bit of background on this idea of searching generative models manifold. So the generative model is learning this synthetic data manifold. And usually when we sample from it, and that's what we've seen until like this point of the presentation, we use this combination of conditional and unconditional signals that I've introduced in the beginning of the presentation. However, there might be other parts of the manifold that we are not reaching when using this procedure. And so how can we better explore the manifold learned by the generative models in order to enable the finding of higher utility data points? So how can we search the generative models manifold? So we could start by searching over the text input space. And so instead of prompting the model with a specific prompt, we could start with a specific prompt, rewrite it in some way, and see what generations come out. So this means that this is what's the procedure that we could follow. So we could start with the prompt. We could rewrite this prompt, for example, by leveraging a large language model, and that way we would obtain n prompt candidates. Then if we use a random seed and these n prompt candidates and feed them to the generative model, we would obtain n image candidates. Among these n image candidates, we could rank them based on some specific score or axis of performance that we care about and only keep the best image. So that way we could search different text options that could yield the best generation that we want to then use. Instead of searching over the input space, we can also search over the random seeds. So this would be similar to the pipeline that I depicted in the previous slide, but instead of having n different prompts that come from the first one, we would have n different random seeds. So here we would fix the prompt and consider n different random seeds. We would feed all of this to the generative model, and we would end up with n candidate images, which again, we could rank and keep the best based on some specific scoring function that we care about. There is also the idea of steering the generation towards desirable properties at model sampling time, and this relies on guidance functions. So this is going to be reminiscent to the classifier guidance that I introduced earlier in the presentation. It's just that in this case, it could be any function. So here, the gray arrow would depict the estimation of the conditional score function that we've seen earlier in the presentation. And then we could use any guidance function that we design that would push the generation towards the desirable properties. It's worth noting that all of these approaches are complementary to each other, and so we could explore them independently or jointly. So let's see some examples of those. So I'll start with searching over the text input space case, and we will do that in order to improve image prompt consistency. So in this case, what we introduced is a framework that we called Opti2I, which is improving consistency via prompt optimization. So exploring the text space in order to find text prompts that would lead to better generations. And so here is the idea of how we did that. So we started with a user prompt. For example, a raccoon wearing formal clothes, wearing a top hat and holding a cane. The raccoon is holding a garbage bag, oil painting in the style of Vincent van Gogh. And we feed this to a state-of-the-art text-to-image generation model. And here are a couple of examples of generations that we obtain. We see that the generations follow the prompt up to some degree, but do not capture all of the details in it. Now, we feed these generations to some scoring functions. So since we care about consistency, in this case, I'm presenting the results on the slide by leveraging the VQA-based metric that was called DSG, Davidsonian scene graph, which I introduced in the background section of the presentation. And so we have that for this specific user prompt, this is the score that I obtain on average in my generations. Now, what I'm going to do is feed this information to a large language model. So we will feed the large language model with informations of tuples, the tuples being the first part being the user prompt, and the second part being the score obtained when leveraging this prompt. And we will ask the large language model to rephrase this prompt such that the score is improved. And we can repeat this process several times. And when doing so, we keep increasing the amount of contextual information that we feed the LLM, because for every new rewriting of the prompt that the LLM comes up with, we are also able to compute the resulting score. This resulting score is always computed with respect to the original prompt, because we are looking for prompt alignment with respect to what the user requested. And so the LLM is only helping us do the text exploration that would find these higher quality or higher consistency generations. And so we can iterate over this procedure several times, and in the end, we come up with an optimized prompt. In this case, the optimized prompt reads as follows. So a cultured raccoon wearing formal attire and the top hat probably holds a cane, while a nearby garbage bag is artistically included in the scene. The painting reflects the vibrant colors and textures of Vincent van Gogh's oil painting. Now, if we feed this to the same text-to-image model, here are the generations that we obtain, which, as we can see on the slide, are a lot closer to the original user prompt in terms of like capturing the details required than the ones that we obtain with the original prompt. And so if we feed this through the scoring function, we see that the scoring function improves. So let's take a look at some of the quantitative results. So here we're comparing the opti-2i framework to a simple paraphrasing baseline. Again, this paraphrasing baseline is also using a large language model, but it's blind to the scoring information. So it doesn't see any score information. It's just trying different prompt variations. Objective here is the scoring function. So on one hand, we have DSG score, which is the VQA-based score to measure consistency. And DCS is a version of the CLIP score that is decomposed into different noun phrases. We use different large language models to do this optimization by prompting, so Llama 2 and GPT 3.5, and different text-to-image systems. We test these on two different data sets, MS-CoCo and Bardi prompts, and we see that performing this text exploration, either with paraphrasing or opti-2i, increases the results with respect to only using the original prompt, and more so when using the optimization by prompting framework. Now, we've improved on the image consistency front, but what happens to quality and diversity? So here we have a bit of results. These are like slightly different metrics than the ones that I have introduced in the beginning of the talk, where FID is a common metric for image generative models that sort of covers both quality and marginal diversity. Precision I have introduced, and recall mirrors precision to compute. It's a proxy for diversity, which is a bit different than coverage. So what we see here is that although we have improved consistency, this has come slightly at the expense of precision and increased recall as well. But this is perhaps unsurprising because all of these metrics are actually based on a reference data set. In this case, for example, the MS-CoCo is grounded on the MS-CoCo real images. But by doing this rephrasing, we're moving away from the prompt that was originally used in the to caption the image CoCo data. And so this means that we might also be drifting from the kind of images that appear in the data set. Here are some visual examples about the results. And so we have the generations from the original prompt for teacups surrounding a kettle, and at the bottom, the optimized prompt with the obtained generation. So 4 teacups encircle a kettle, forming cohesive and picturesque tea setup. So we see that although the generations are still not perfect from a consistency perspective, they more closely follow the original prompt than the ones on the top of the slide. And here is the same example that I started the discussion with, the example of the raccoon, and we see that after rephrasing the prompt with the Opti2i framework, we also improve the image generation consistency. So for now, we've seen how we can do exploration over the text space in order to improve text image consistency. Now let's move towards a different dimension that we care about, which is diversity. And so here what we're going to do is steer the generation process in order to improve representation diversity. So what we do here is what we call improving diversity with contextualized Venn score guidance. So recall that classifier guidance uses an external classifier in order to steer the generation towards the direction that maximizes the log likelihood of the conditioning signal. So what we do here is we build on top of this idea and extend the guidance toolbox of the diffusion and flow matching models by introducing the Venn score guidance. Venn score is a metric of diversity that does not require grounding on a real data set. And what it does intuitively is trying to assess the effective number of examples within a data set. And so it does that by computing similarities in some embedding space between different points in the data set, and then computing the rank of these similarity metrics. And so here is what we did. So we start with the conditional score function. So this is the case for diffusion models, but can be translated to flow matching too. We start with the conditional score function. So that would be the gray part of the equation, or the gray arrow. And we modify the step that we want to take, that we need to take with the gradient of the Venn score. So here we need to keep a memory of what we have generated so far. But let's see this in a bit more detail. So when we generate from a latent diffusion model, we use some noise and a prompt, and we obtain a generation. And this is the kind of diversity that I've shown you earlier in the digging indicators for cars. So the top row would be car in Africa, and the bottom row would be car in Europe. Now, what we do is we keep a memory bank of generated images. So every time we generate an image, we add it to this memory bank. And during generation, we add this guidance term that tries to maximize the dissimilarity between the image that we are generating and the ones that we have generated so far. So intuitively, this Venn score guidance is maximizing the effective number of the similar examples. And this is the kind of diversity that we obtain. So we see that using this, we can increase the diversity of the generations, but we don't do it necessarily in the desirable way, or the way that we would want to increase this diversity. So to address this, what we do is add some exemplar reference images to capture the kind of data that we want to generate. So now we have two things. On one side, we have this memory bank of generated images, and we keep adding the new generated images to it. And on this other hand, we have a subset of real data, which we call exemplar data, that we also feed to the Venn score guidance and call the result contextualized Venn score guidance. So now what we want to do is make sure that the generations that we perform are as dissimilar as possible to the ones that we have generated so far, but we want to do this in a way that the generations remain close in style to the reference images that we are providing. And so intuitively, contextualized Venn score guidance is maximizing the effective number of the similar examples while keeping them close to a small set of real images. And this is now the kind of diversity that we obtain. So we see, for example, on the bottom row, instead of having only urban scenes, we start seeing some rural environments too. So let's take a look at some quantitative results. So here we are comparing contextualize Venn score guidance with prior art, including the baseline where we just sample from the model in a vanilla way, which would be LDM, so the first bar. And we're doing this comparison in terms of F1 score. So F1 score is the harmonic mean between quality and diversity metrics. And so what we observe here, so the bars have two colors. The part that is non-gray depicts the average obtained in F1 score across different regions, and the gray part shows the maximum F1 obtained, so the region that yielded the best F1 score. So what we see here is that when using vanilla sampling for LDMs, we have like among the lowest F1 score. This score is only worse when doing rephrasing of the prompts using synonyms. But when using large language models to do this rephrasing, we can improve the results. However, like if we compare all of the previous works to the contextualized Venn score guidance, we see that contextualized Venn score guidance not only boosts the results substantially on average, but also results in among the lowest disparities across region when compared to previous art. So here are some visual results for vanilla sampling of the model on the left and contextualized Venn score guidance sample images on the right. And if we zoom in to the first row, for example, this is the case of cooking pots in Africa before the contextualized Venn score exploration and after it. We see that after the guidance term is added, we obtain samples that are not all in outdoors environments. We also see indoors environments, and we see a lot more variations when it comes to the shapes and state of these objects. So now we've seen how to explore the text space, how to steer the generation process and explore through guidance to improve diversity. So now let's see how to steer the generations in order to improve overall utility. So what we did in this work is what we introduced is the chamfer guidance. So we extended, again, the same idea. We extended the guidance toolbox of diffusion and flow matching model and introduced chamfer guidance. So what is chamfer guidance? Chamfer guidance is a metric commonly used in computer vision, in 3D computer vision, and it measures the distance between two sets of points. So in our case, we measure a chamfer distance between a handful of real images in some embedding space and a set of generated data. The embedding space that we use to compute the chamfer distance is the DynoV2 embedding space. And chamfer guide, maybe one interesting feature about the chamfer guidance is that it can be used without the classifier-free guidance. So this is interesting from the perspective of a computational complexity at sampling time. So here is the formulation. So first we have the chamfer loss on the bottom. So this has two terms trying to match one set of points to the other and vice versa. And then we have the updated step that we will take when doing the sampling process. So again, we have one term, which is the conditional score, and then we add the chamfer guidance. Maybe by contrast to the Venn score guidance, we see that instead of an addition, we have a subtraction of the term. This is because in the case of the Venn score guidance, we wanted to maximize the Venn score, so increase the dissimilarities between images. Here we want to minimize the chamfer guidance, so we want the set of generated images to be as close as possible to the set of real data that we have. So let's see some results when it comes to geodiversity. So this is the same bar plot that we've seen in the context of contextualized Venn score guidance, just adding the results of chamfer guidance too. So we see that chamfer guidance further boosts the average F1 score on the GeoD dataset. However, it results in slightly bigger disparities across regions than the previous method. still compared with the state of the art, it's reducing the disparities across regions substantially with respect to most methods. Now, for this chamfer guidance, we took it a step further and we went to this idea of really validating the utility of the synthetic data for downstream training. And so here it's, I'm going to show results for the ImageNet dataset. So we're going to use samples from the text-to-image model. In this case, we have two versions, so Stable Diffusion 1.5 and 3.5. So we're going to prompt the model with ImageNet classes and get samples using vanilla sampling, but also using the sampling process and using the chamfer guidance. So first, we can look at the qualitative results. So we can compare base, which would be the generations obtained with vanilla sampling, so no exploration of the manifold, and chamfer guidance. And for grounding, I have like some images of the dataset for the same class. So we see that the diversity and the representation of the specific class is enhanced with the chamfer guidance, with a lot more different backgrounds that are maybe more reminiscent to what we have in the dataset, whereas for vanilla sampling, we have something that is very similar across generations. Now, if we go back to the bar plot, here I'm reporting results for ImageNet 1K and versions of ImageNet that are considered out of distribution. And it's in terms of, results are reported in terms of accuracy. So here we use 2,000 real data points for the chamfer guidance. And so we will compare results of vanilla sampling using version 1.5 to chamfer guided results. So we see like these are like the two first bars on the slide, and we see substantial improvements. Remember that the most recent version of the latent diffusion model, 3.5, yielded worse results. But when coupling this with chamfer guidance, we see that results on ImageNet are now on par with those of the earlier versions. Then we can compare these with training a classifier with the 2,000 examples that we used to obtain the generations in the chamfer guidance case. And we see that results of training a classifier on 2,000 data points are substantially worse. However, of course, if we use the full ImageNet dataset with 1.3 million data points, real data points, we cannot match its performance with synthetic data. And we see similar trends for the out of distribution data sets, except for some data sets where synthetic data can match the performance of real data. So now that we've seen how to explore the manifold of image generative models through text exploration and through guidance mechanisms, correcting the trajectories towards some desirable properties, let's see if we can do something similar in the video generation domain. So let's focus on steering generation trajectories and searching over random seeds in order to improve physics plausibility. So let's start with some motivation. So state-of-the-art video generative models, although they generate visually pleasing content, they frequently violate basic physics laws. So on the other hand, we have latent worm models, and I'll cover one of them later in the presentation. These latent worm models are different kinds of models that have demonstrated to have strong capabilities in physics understanding. So the hypothesis, again, here will be that there exists physically plausible videos in the manifold learned by the generative model, and it's about properly exploring the manifold in order to find this high utility data. So the key idea here is that we will leverage the properties of the latent worm model. We will leverage the latent worm model as a reward signal to steer the generations and search for samples that have improved physics without retraining the video generative model. So it's a very similar idea than the ones that we have explored in the image domain. So how we do that is we leverage VJEPA2 as a latent worm model. VJEPA2 is a video joint embedding predictive architecture. It's a video self-supervised learning model that is composed of a context encoder and a predictor network. Unlike generative models that predict pixels, VJEPA2 predicts latent representations of masked video region from unmasked ones. VJEPA2 is trained to minimize the prediction error in the latent space, and by doing so, the model learns to ignore pixel noise and focuses on underlying spatiotemporal dynamics, such as object permanence and trajectory continuity. So let's take a look at what it means to use VJEPA2 as a reward model. So first, we take our video generation model, generate videos from our conditionings, and then we apply a sliding window approach. This sliding window approach splits the generated video into two sets, a set of context frames and a set of future frames. We encode the generated context and predict the embedding of the future, and we do that with VJEPA2. So we take the context, we feed it to the VJEPA2 encoder, the result, we feed it to the VJEPA predictor, and we see what is the prediction of the future according to VJEPA. Then we take the generation of the future from the generative model, encode it with a VJEPA2 encoder, and now we will compare what our generative model has generated as future with what VJEPA predicts as future for this video, given the context that it has seen. So in order to do this comparison, what we do is we compute what we call the surprise score, which is the cosine similarity between the embedding of the generated future frames and the VJEPA2 predictions. So now that we know how to compute this surprise score, we will use this surprise score in two ways. The first is that we will, following what we've done in the image domain, we will extend the guidance toolbox of video generative models with VJEPA2 surprise score. So once again, we have the conditional score, which we complement with the minimization of VJEPA2 reward, so the minimization of the surprise score, which is a function R on the slide. So this allows us to explore the manifold learned by the video generative model, and we combine the guidance-based search with random seed selection. So we do that by sampling n VJEPA-guided samples from the generative model and picking the best one according to the surprise score. So we pick the one that has the lowest surprise score. So let's take a look at some numerical results. So here are results on the physics IQ dataset. This is a dataset that is built to test physics of models such as video generative models. We see how many state-of-the-art models perform on this video. And now let's focus on our CogVideo X baseline. So we have a baseline that we use to compute results on physics IQ score. And we couple this baseline with our search mechanism. So we endow the baseline with our exploration mechanisms, and we are able to boost the results by more than 5%. Then we take a second model, which is a state-of-the-art model that is multi-frame conditioned, which is the McGill model. And again, we compare its baseline results when using its vanilla sampling methodology and when endowing the model with our searching capabilities. And so what we see here is that, again, we can boost the performance of the model by more than 6%. And here are some visual results, some qualitative results. So on the left side, we have vanilla sampling. So that would be sampling from the model as is. And on the right side, we have the result of sampling with search. So that would be leveraging VJEPA2 as guidance signal, as well as leveraging VJEPA2 to search over seeds. So what we see is that this leads to improved physics. So we can see how the tiles are falling in the top row, or how the ball is not bouncing back in the second row, or how the cup is deformed by applying pressure in the third row. So now that we've seen how we can do this exploration of the manifold for image generative models and for video generative models, we have seen how we can improve some of the desirable properties of these models, but we have mainly focused on properties that are either on the consistency space, the diversity space, or the overall utility that we have defined as important high utility access. However, if you remember from the beginning of the presentation, there was this idea of tailoring the synthetic data to the needs of the learner, and this is something that we haven't covered yet. So I want to spend a few minutes discussing this part. So now we'll go back to the image domain and see how synthetic data may be tailored to the needs of the learner. So in the beginning of the presentation, I showed you this diagram where we had the data generation model and the machine learning model. And so there was no feedback signal from the learner to inform the generator of the kind of data that it needs to learn. So instead, what we can do here is try to provide this feedback from the learner to make sure that the synthetic data that we collect is beneficial for its learning. So again, we have the data generator. The data generator provides an infinite data source that can be queried by steering the model to generate useful images. And then on the right side, we have the learner, which is, again, any machine learning model you can think of, vision-based in our case. And this model is data hungry, as we have seen earlier. But in this case, it has the ability to come up with queries to gather data. So it never stops learning, and it uses its acquired knowledge to decide what is useful to improve its own performance. So let's see a possible implementation of this framework. So as data generator, we take a pre-trained state-of-the-art diffusion model. As image classification, we take an image classification that is trained on real or synthetic data. And as query mechanism, we will use feedback-guided sampling. So again, this is the same idea that we used to explore the generative models manifold to come up with samples that were higher diversity and quality in the case of the chamfer guidance. But now what we care about is samples that are high utility for the downstream model training. So in this case, for the image classifier that we want to train on our synthetic data. So again, we will extend the guidance toolbox of diffusion models, in this case, with a criteria that it comes from the learner. In our case, what we did is we had like this image classification model, and as criteria, we used the entropy. So in other words, what we wanted to generate were images that were high entropy, so sort of difficult for the model in training, so for the image classifier in training. And we did that following guidance again, so steering the generation process towards images that were high entropy for the classification model in training. And so again, we altered the conditional score function by plugging in this criteria, which is the entropy of the model being trained, the entropy of the classifier, which we want to maximize in this case. So now we use this idea of feedback guidance to build curriculums of synthetic data that are tailored to the learner. And that's what we called deliberate practice. So we start with a pool of initial synthetic data and train our classifier. While we do that, we monitor the validation accuracy. And whenever we see there is no more training, no more learning, so the validation is plateauing, we generate new samples by leveraging feedback guidance. So these will be samples that are at this moment in training, high entropy for the classifier being trained. Then the newly generated samples are added to the data set and training continues. And we keep doing that a few iterations. So here's what happens. So on the x-axis, we have the training iterations. On the y-axis, we have the accuracy of the image classifier being trained. So we start with a set of synthetic data, and we start training the classifier. So that would be the orange line. And once the validation starts plateauing, we stop, and we collect data from a generative model data that maximizes the entropy of the classification model. Then we add this data to the pool of training data, and we keep continuing. So we keep training. So this is the bifurcation that we see here between the orange line and the purple line. So adding this additional, more challenging data boosts the training, boosts the validation accuracy until it starts plateauing again. Then we'll stop again and repeat the same procedure. We'll collect additional data from the generator. That will be data, again, that is high entropy for the classifier at this new moment in time. And this will, again, boost the validation accuracy and until a moment where it will plateau. And so the result of doing that is the following. So I'm reporting results here for the ImageNet 100 and ImageNet 1K, and I'm comparing the results with the results that I showed you in the beginning of the presentation about the scaling loss of synthetic data. What we see in both cases is that by leveraging this feedback signal from the model being trained from the image classifier to the generative model, we can improve the scaling loss of vision synthetic data in both cases. So leveraging high utility or more useful synthetic data to train our model, our image classifier, improves the performance while requiring substantially less data than what we did before. So if we look at the plots to achieve the accuracy that was the sort of maximum, or like the plateau accuracy that we achieved before, we can get there with substantially less data. Now, if we compare with prior art, so here we're reporting accuracy for ImageNet 1K and the out-of-distribution ImageNet data sets. So we compare DP, which stands for deliberate practice, so these curriculums of synthetic data tailored to the learner, with prior art. And we also compare with the baseline using the full ImageNet data set to train on the image classifier. So of course, results are still below using a huge amount of real data when it comes to results for ImageNet 1K. But what we see is that with deliberate practice, we can improve slightly on ImageNet 1K with respect to other models, but more substantially for out-of-distribution data sets. So this showcases the kind of examples that are generated at different stages of training. So we have initial data at the beginning of training. We see a lot more uniformity in terms of the kind of colors of the generations. And then on the right side, we have the final accumulated data at the end of training. So we see a lot more variability, especially in the backgrounds, but also in the poses of the object of interest. So I'll conclude this presentation with the following takeaways. So what I hope to have convinced you is that there is a lot of interesting knowledge that is hidden in the manifold, that the synthetic data manifold that is learned by visual generative models. And that signal from synthetic data may be used to complement that of real data during the training of machine learning models. So far, what we've seen is that vision synthetic data has shown to be useful when real data is scarce. However, synthetic data still falls behind real data when we have huge amounts of real data to compare to. Better exploration of the manifold learned by the generative models hence holds the potential of resulting in samples that exhibit the desirable properties and that can reduce the gap or further reduce the gap between real and synthetic data. However, further research is needed to fully close this gap. Once we unlock efficient and effective ways of learning from synthetic data, we can envision to witness a step change in model capabilities. I cannot end this talk without highlighting all of my collaborators with whom all of this work that I presented wouldn't have been possible. And with that, I'll wrap up the presentation and I'll take any questions you might have.
Thank you very much for this wonderful talk. Participants, if you have any question, you can ask now.
I have a few questions. Is there any? But first, let's see if the participants have something on the chat. Nothing as of yet. So, Adriana, it's a wonderful talk and a series of very nice works, no doubt. I have just a few queries, like in this Op2I framework that you showed. How does it exactly ensures that the LLM guided prompt optimization will not simply overfit to the scorer's checklist, thereby optimizing for, let's say, superficial attribute matching, rather than improving the underlying semantic alignment between the prompt intent and, let's say, the generated imagery that you're showing?
Sure, I can start with this question. So yeah, thanks for the thoughtful question. So maybe something to be noted here is that all of this happens at test time. So this is not something that we are training. So we're just using the LLM out of the box to come up with new prompts and explore these text prompts to see which one would result in the highest consistency generation with respect to what the user has requested. This also touches on how reliable this scoring function is. And I agree that this procedure could be sensitive to what has been learned or not learned by this scoring function. So I think like our goal here was to provide a proof of concept of how we could do optimization by prompting, and we tested that with a couple of typically used scoring functions in the community, right? That would be one based on clip score, which we know has some problems, for example, in capturing negations or like attribute binding or other things. So those are places where the scoring function may be misleading when it comes to choosing like the best generations. And the same for the other metric that we use. So this is the VQA-based metric, the Davidsonian score, scene graph score. Again, it's one of the metrics that is commonly used, but it's based on a VQA model, which is trained on some data, has its parts of the data that it has learned, has its biases too. And what we do see when using these metrics is that it often happens that the metric will quickly assign very high scores that are close to 100%, even though not all of the details are captured in the generations. But again, going back to the idea of the proof of concept, the idea is to have this framework, and as the metrics get better, this like the scoring function could be changed to improve the process.
Yeah. That kind of clears the confusion. I had another sort of from this VJPA 2. I mean, you were talking about the surprise score as a reward. The question is how exactly this surprise score can, let's say, reshape the generative model's sampling trajectory in a latent space. And what guarantees, of course, if any, is there any such guarantee that exists for, let's say, optimizing for surprise will yield videos consistent with the physical world dynamics rather than merely amplifying the unpredictable or high entropy artifacts?
Yeah, so okay. Yeah, thanks for the question. Again, very thoughtful question. So I'll just try to address like different parts of the question. So first, the way we use this surprise score, the way that we implement it is first we assume that because VJPA 2 is a word model which has shown, a latent word model which has shown to have good intuitive physics understanding, that it will be like that its predictions, its future predictions will be more reliable than the ones that we see for video generative models, where we know that physics is a challenge, right? So we are assuming that we're using our VJPA 2 model as the source of ground truth. Of course, it's not going to be a perfect ground truth, but this is how we're using it. So you were using it in two different ways. So let's start maybe with the simplest way, which would be a search over random seeds. So in this case, you can think of the procedure as follows. You just take samples given a conditioning from a state-of-the-art video generative models, and then you just rank the generations based on this surprise score, and you select the generation that yields the lowest surprise score. So that would be searching over a bunch of random seeds and they taking the best of the generation, so best of n kind of procedure. So this is essentially reminiscent to all the well, it would be like VJEPA as a judge to select which random seeds are the ones yielding the highest plausibility in terms of physics from the VJEPA2 perspective. The second way that we use it, which is by altering the trajectories of the generations, is by altering again, the guidance toolbox of diffusion models. So most state-of-the-art models in video generations rely on diffusion or flow matching models. Some of them are autoregressive, but within the autoregressive steps, they diffuse parts of the temporal component. And so we can, within these chunks that are generated with diffusion or flow matching objective, we can, same way that we did with images, alter the score, the conditional score function by adding whatever guidance term we come up with, right? And so the guidance term that we plug in here is the VJEPA2 surprise score. So while we are denoising, so during the generation process here, we will alter the trajectory that we follow at sampling time, so that we push the generations, the final generations, to be closer to what VJEPA2 predicts. And then to answer the, I think, last part of the question that you had, which was whether VJEPA2 is actually modeling physics. So we have no guarantees on that. So it's more like the assumption that because of how VJEPA2 is trained, it's trained to predict the future. And there is a correlation between being able to predict this future from videos where we know physics are consistent because data sets of real videos, and intuitive physics plausibility. So this won't work for every single case. So we have examples in the paper where we see, for example, when it comes to materials, that this is not as straightforward for VJEPA2 to predict, and in such cases it will fail. But in other cases, like the ones that I've shown in the presentation, it works pretty well. So I think exploiting this intuitive physics understanding that is captured in VJEPA2, but there is no guarantee that we will be able to improve all kinds of physics scenarios.
Yeah, so I was just trying to understand these theoretical implications of mixing the log likelihood or conditional likelihood or the curiosity-like reward term that you are using. But yeah, I mean, your explanation helps in that. Okay, so if there is any more question from the participants, please. Divanjan, can you see the chat?
No, I think there is nothing on chat.
Okay, so if there are no more questions, let us thank Professor Adriana once again for this wonderful lecture. And that is the end of this session. Thank you, Adriana. Hope we will again meet in some future session or some future conference sometimes. Thanks a lot for sharing your expertise.
And thanks for the invitation. It was my pleasure to share all of this with you today. Thank you.
Thank you.